Hello, everyone, and thank you for joining us today. I am your host, Shannon Hicks, and welcome to the webinar, Using Electrical Signals to Evaluate and Monitor Motor Durability. Now, before we begin the presentation, I would like to review a few housekeeping items with you. Please take a moment to observe the tools available in the WebEx event window. Now, all participants' microphones are muted during the webinar. Please do not forget to activate your PC speakers to enable audio or connect headphones to your PC. You may have to take the step of joining the audio conference to hear sound. Please type any questions you have into the WebEx Q&A dialog. You can open the Q&A window by selecting the Q&A icon in the WebEx toolbar at the top of your screen. Today's presentation will be emailed to all attendees. The webinar will also be posted on our website. If you have additional technical questions, feel free to contact our technical support team at support@us.hbm.com. Now, today's presentation will be presented by Mitch Marks. He is our business development from electrification. He has a BSEE, MSEE from the University of Wisconsin. He joined HBM in 2017 with previous positions in motor manufacturing, controls, and testing. I will now like to welcome Mitch Marks to begin the presentation.
All right, cool. And Shannon, you can hear me all right?
Yep, you're great.
Cool. So today we're going to be talking about using motor measurements and electrical measurements for looking at the electric and magnetic durability of machines. I'll be honest, I'm not a durability expert, and I'm sure there's a few of you on here. So I'm hoping to open up your eyes to some of the failure modes we see in motors. I'm not going to cover inverters, but they are similar, and the methods for monitoring them are similar. So be nice in the Q&A. I hope to introduce some stuff and open your eyes to some possibilities for looking at the electrical failure modes and identifying mechanical failure modes with those. So we're going to start out with the basics, durability and durability testing, failure modes in electric machines. This is not an inclusive list, but these are the big ones. Challenges in durability testing for electric motors. It's not the easiest thing. Using electric signals to monitor motor durability, measuring, and then the HBK solution, because there's no free lunch. And if you guys stick around, you get to see why I was taking a torch to a motor rotor. So that's your incentive for sticking around the whole time. So durability testing, as a lot of us probably know, products fail in the field. And with some intelligence and with some knowledge of the use cycle, we can use lab tests to replicate these failure modes. And then once we understand these failure modes, once we can replicate them, we can understand that product life cycle and use tools to design a longer life cycle for the given operation. So traditional powertrain durability testing, we want to identify the likely failure mechanisms. So for example, we're going to take a car out on the road, identify what its torque and speed profile is, and this is some actual road data for torque and speed from a Chevy Bolt. We're going to take that real world data. We're going to use it to create a torque and speed profile for a vehicle. And then we're going to want to try to accelerate those tests in the lab. So we go from that in service, that damage in service, and then we go to the lab and we try to replicate that with a predictive profile or an accelerated profile. And this can be done by using higher than normal loading, using higher than normal frequencies, or higher than normal temperatures. And this is where things start to get difficult with electric motors, as we'll touch on in a little bit. And then at the end of that, after we've identified our road fatigue, we've identified our in-lab fatigue methods, we're going to want to do a teardown and comparative analysis of how these things have degraded, how these components have failed. So we're definitely going to see this theme continued into the electrics. So the questions that arise for lab durability testing are, how long do we test for? Given my product's life cycle, given my product's profile, how long do I test for? What are the loading conditions? What are the temperatures? How much torque, how much speed? What is the ramp rates? And then how many samples? What am I measuring and how frequently do I need to measure to understand these fatigue modes and these failure modes? So these are really the questions that we're hopefully going to look to answer today on the electrical side. I'll trust the experts for the mechanical side. So what are some failure modes in electric motors? And I think this will be a little fun. First, we need to kind of go to the breakdown of what our permanent magnet motor construction is. If we're looking at automotive, we're looking at aerospace, permanent magnet is the top dog right now. But a lot of the things we're going to talk about do pertain to other motor types as well. So we take our stator. This is the stationary part. We have a laminated core. So we have these thin sheets of steel that create this stator core. We have the windings. In this instance, this is from a Chevy Volt. It's got a bar wound rotor, but we have these copper windings. We then have, rotor hub, bearings. We have the rotor laminations. Again, these are thin sheets of steel that are stamped, pressed together. And inside of those rotor laminations, we can see we have a little skew here to reduce cogging torque. We have the magnets inside of it. In this exploded view, we have these magnets. And then we have more bearings, protective plates. And if we look at this is a pretty simple construction. We have laminations, we have copper, we have bearings, we have rotor, we have magnets. And what the failure modes we're predominantly going to see are in the bearings, because they're rotating, in the magnets, because they're susceptible to thermal stresses, and in the windings, because they're also susceptible to thermal stresses. So those are kind of the three topics we're going to touch on today. So, kind of reiterating what I just said, if we look at the electric machines, what are the faults we're going to see? And again, these are kind of focusing on the more electric magnetic side. We have two categories, stator faults and rotor faults, stationary part, rotating part. And in the stator, we have terminal short circuits. That could be at the inverter, that could be, from winding to winding going to the machine, but this is short circuits before it gets to the motor. We have open circuits, or maybe the windings separate and we no longer have current going through it. Or the real fun one, and this is exciting, is turn-to-turn shorts, or inter-turn shorts, where maybe windings from two phases short together, windings from multiple coils short together, or just windings next to each other short together. And when you have shorts, you have big currents, you have heat, you have really exciting events. On the rotor side, we have electrical failures and mechanical failures. And the electrical failures are going to be broken cage if you're working with an induction machine, broken magnets. This is often on insertion or if the machine is feeling a really rough profile, or demagnetization. On the mechanical side, we have eccentricities, which is, the rotor becoming uneven, misalignments, and bearings. And if we look at a study performed by IEEE and EPRI, the Electric Power Research Institute, we see that the failures in motors are really largely bearings. We got about 40% are bearings. Depending on who you're talking to, 25 to 40, 35% are stator failures. Rotor failures are low, but they, not negligible, 10, 15%. And then other is in the life of rotating machinery, everything else that can happen. So we're going to focus on kind of the bearings, the stator, and the rotor. And fun fact here, it can take less than 2 seconds for an inter-turn short to really permanently damage a machine. So these happen fast. So if we can predict them earlier, there's a lot of value in understanding that, or understanding why it could happen very quickly in 10 seconds from now, 20 seconds from now, 50 seconds from now. All right, so let's look at the first one, bearing currents. This was the most common fault type. So the fault is voltage on the rotor discharging through the stator, through the bearings to the stator. And my little diagram here, I have my rotor shaft, I have my bearings, and what happens is that we have this high frequency on the stator, and that's capacitively coupling to the rotor. And there's a little current transferring from the stator to the rotor. On the rotor, this charge builds up. Basically, we're going from 0 voltage difference from the stator to the rotor to that rotor voltage is creeping up. Maybe it gets to 4, 5, 6 volts. We have an event that happens in the bearings. Either the bearings touch and become conductive, or the fluid has a capacitive breakdown, and that voltage on the rotor discharges through the bearings to the stator. So we actually get currents going through the stator. This is kind of a long-term failure mode because this is happening frequently. It's happening a lot. We have common mode currents that are coupling to that rotor. These couplets are going to ground through those bearings, and it's caused a lot of times by rotor eccentricity. If it's not even, we get that contact in the bearings. So why is this bad? Why are currents coming from the rotor to the stator through the bearings bad? Well, currents create heat. Heat creates problems. So I actually see fluting in the raceway of the bearing. If you look at a picture of a bearing with fluting on the raceway, there's little pits, and this is going to cause the bearing to not roll as good, or it's going to create flat parts and going to create bumping and more eccentricity. So we're kind of going to cook that fluting, or we're going to cook that raceway and flute it. If the bearing has fluid in it, you could effectively cook the fluid, and now you're no longer getting the really good protection that you were looking for. If it's ball bearings, the bearings themselves can become flat on edges. And again, you kind of get that it's no longer operating as good as it can. And this is going to create heating. This is going to create more fault or more short circuits, and it's going to be a increasing failure until you have a catastrophic failure. Ultimately, again, resulting in bearing failure. And again, this is voltage building up on the rotor, discharging through the bearings to the stator. That's bearing currents. Inner turn shorts and terminal short circuits. As I kind of introduced in the previous slide, this is my electrical diagram of a motor. This is a 3-phase motor with a neutral. And we can have a variety of short circuits. So we can have coil-to-coil shorts, where the lamination between 2 windings shorts together, we get a fault path. We have turn-to-turn shorts. Again, this is just where the fault is happening between where in the coils. We could have phase-to-phase shorts, where phase A and phase B get shorted together. We could have coil-to-ground, where maybe the copper winding shorts to the stator housing, shorts to the laminations, and then we're getting a current there. Or open circuits, where they're not touching at all. So what's the fault? Winding short together or to ground. We have a breakdown of the winding enamel that results in this, and you have a short circuit which creates a really large current going through a direction you don't want. So what are the causes? Well, that's mechanical stresses. We have vibrations. We have things rubbing against each other. Maybe we have a fluid-drenched stator, and we get some particulates in there that are causing wear and tear. We have electrical stresses. If we're experiencing voltage overshoots, that enamel could break down and we get, a kind of a partial discharge, a corona discharge. Or probably the most likely culprit is thermal stresses. These windings get too hot, the enamel breaks down, and we create that short between those 2 windings. We get those large currents coming through. We have more heat, we have more enamel breakdown, we have more heat, we have more enamel breakdown, we have a catastrophic failure. And what's the effect? Well, we have inefficiency because we have power now not going where we want it. We have potentially demagnetization, which is the failure mode we'll touch on next. And in a lot of cases, smoke, fire, all the really nasty stuff we don't want to happen. And here's just an example, and I probably should have saved this diagram for a later slide. But if we have a fault current, let's say we have 2 windings shorted together, we get that fault current. This is from 1% faulted to 100% faulted in a given coil. We can see that the currents don't change all that much. But for a little bit of fault, we have a little bit of torque disturbance. And for a big fault, we have a lot of torque disturbance. So even a little fault can create a really big torque disturbance, can cause a really big problem. So you're now experts on inner turn shorts. Basically, in that stator, windings get shorted together. They create big currents where we don't want them. They create heat where we don't want it. Not that we ever really want heat. All right, demagnetization. I think this one's pretty fun. So the fault is that the magnets lose their strength, or that the magnetic shape changes. So let's say I want my magnet shape, like how I see the magnet flux in the air gap, to be a sine wave, and now it's kind of a pump wave. Like that would be changing the magnet shape. The flux profile doesn't look how we expect it. And these can be symmetrical, where all the magnets are demagnetized equally, or asymmetrical, where one magnet is demagnetized more than the others. And when I talk about demagnetization, I kind of need to go down a little bit of the magnet rabbit hole, so I hope I don't lose anybody. But if we look at a magnet, this is magnet field intensity. This is kind of the current coming from the stator versus the strength of the magnet. So if I have a permanent magnet, this is how strong it is. And if we put negative current into the air gap at that magnet, we're going to make that magnet look weaker. And we have this normal operation point here where, all right, if I put negative 500 amps at that magnet, it's going to decrease from 1 per unit to 0.5 per unit. But then it'll recover when I take that current away. So we have that recovery. This is normal operation until we hit this knee point. So if I put negative 800 amps in that air gap, I'm going to push that magnet beyond that knee point, and now I can't recover. And if I push it far enough, I can then recover back to this lower magnetic state. So we can actually change how strong that magnet is on the fly. We can use this to our advantage for things like field weakening, but we can also go too far and turn our rotor into a paperweight. So this is what, when I say demagnetization, it's really making that magnet so that it's a paperweight. It's no longer a magnet. And that's a catastrophic failure for a traction motor. So what causes us to go beyond this knee point? What causes us to create that critical failure demagnetization? Well, overheating. It's called the Curie temperature. The Curie temperature for a neodymium magnet is, between 100 and 220 C. If we get to these temperatures, we're having a really hard time, keeping that magnetization. We have conflicting magnetic fields. If I put too much negative current at that magnet, I'm going to cause demagnetization. And if we have stator faults, funny enough, these stator faults can cause very large negative currents and create demagnetization. And what's the effect of demagnetization? Well, torque ripple, we kind of no longer have that profile we're expecting. So we're going to get dynamic torques. If anybody was betting how long it would take me to say torque ripple, that's how long it took. We're going to have reduced power. We no longer have all that flux coming from the rotor, so we're not going to be able to produce as much power. And we're going to have unbalanced line currents and voltages. We're going to see a pretty dramatic change in what that back EMF looks like, and therefore what our voltages and currents are that we're experiencing. So this one is really bad because we're losing power. We're losing power to the machine. And as we'll see later, a little bit of demagnetization makes a big change in the power output. All right, so I hope I didn't go too fast for those. There's a lot of literature that I referenced. If you want to learn more, I'd be happy to take anything offline. But what are the challenges for durability testing in electric motors? Well, it's hard to accelerate. I mentioned that Curie temperature. I mentioned that the windings are thermally limited. I mentioned that the bearing currents don't necessarily like those high temperatures. If I'm running a durability test and I want to look at the actual operation profile, I can't really run that motor hot because those temperatures are going to cause demagnetization prematurely. And the high temperatures are going to drastically alter the efficiency and the performance. So I almost have to run in the operating temperature. So we can't accelerate as much as we would with a traditional transmission or gearbox. Another challenge is, and I'm sure this translates to many other industries, but every motor's failure modes are a little unique. We have very different magnetic patterns. We have very different winding patterns. We have very different material properties from magnet to magnet even, or from winding to winding. So each one's a little bit of a unique butterfly. I don't think this is that different from traditional durability testing, but it is something to consider. We can't treat these as one size fits all. It's really difficult to measure rotor temperature. And when we think that the magnet failures are largely driven by that Curie temperature, and that Curie temperature is local to the rotor, if we don't have a good way of measuring rotor temp, that becomes hard. We have to use mathematical estimations, and there's inherent error. HPK does have some cool methods for measuring rotor temperature. I'm not going to talk about them today, but if you're serious about it, I would love to have that discussion. It's a very electromechanical system. An inverter, this fast switching electrical device, is causing magnets, which is causing torque and speed, which is causing vibrations, torque ripple. And we have this issue of electrical influencing mechanical and mechanical influencing electrical. So we kind of get this parity of we almost need to know how one is acting to understand why the other is. This bearing failure, mechanical failure, is being caused by high currents running through them. This winding turn-to-turn shorts is caused by a temperature, a vibration. So we have that mechanical affecting that electrical. So it's just something to consider that we need to see the whole picture. Now, these tests are running for, tens to hundreds of days. And these electrical failures are very high speed. They're happening in the kilohertz rate. So we're looking for high-speed events on very long time scales. That's always a challenge from a data perspective. And just the long test durations result in some challenges from a data perspective. So these are some of the challenges. Now, how about some solutions? So using electric signals to look at that motor durability in those failure modes. I'm going to go through those 3 examples I gave. How do we measure bearing currents? Now, this is from an old textbook. It's got everything you need, but it's not the easiest to interpret, so I'm going to walk through it. We have our stator that is highlighted by this outside slashed lines. We have a rotor, the inside slashed lines. The winding is kind of this cutaway here on the ends. And these bearings are this lot of slashes going on. So we can measure the common mode current. We have 3 phases coming into the motor. If we put a current sensor around those, or we have individual current sensors and sum them, we can see how much common mode current there is. So if we understand that common mode current, we can start to understand what's leading to voltages coming from rotor to stator and then from stator to ground. So we can start to see where these bearing currents are coming from. So we can measure that common mode current. Cool. We can measure the bearing currents IB. So again, if this is my bearing, I can see this little black dash here, I can put an isolation, electrical isolation between my bearing and my housing. I can put a conductor from my bearing to measurement or to ground and then measure that current. I can measure that bearing current. That's awesome. I can also measure my bearing voltage. This one's a lot easier. I just put a measurement on the bearing and a measurement on the housing, and I look at that differential. So we can start to understand what is my bearing voltage, what is my bearing current. We can see that voltage creep up over time, and then we can see it discharge through the bearing, creep up, discharge. And we can start understanding what are the currents that bearing would experience. We can measure temperature. As these bearings start to cook, their temperature is going to increase. And we can start to see, all right, I have this frequency of currents coming through my bearing. I have this temperature. It's really cool stuff. And we can look at increases in frequency of discharge or increases in amplitude of discharge in accordance or in parallel with increased temperatures. And again, identify that degradation over time and really see how that bearing behaves, how my total efficiency behaves. We can understand this whole system. Again, I think this is pretty exciting stuff, given that 40% or so of motor failures are coming from bearings. With a little bit of engineering, we can do a pretty good job at understanding what's happening. Inner turn shorts. These are, again, the 2 windings in the stator getting shorted together. So when you short 2 windings together, you get big currents. Big currents mean there's stuff we can measure, so that's cool. We can measure current disturbances. We can look at what we call the zero sequence voltage. That's basically what's not useful, where are currents hiding where they're not useful. It's a mathematical transform we use to look at basically what the neutral currents are. So we can look at that zero sequence voltage or current. And in my example down here, I have normal operation of zero sequence voltage where we see that black line, not a big sine wave. And I have a couple different faults, and we can see a really big zero sequence, or negative sequence voltage and current. So this is pretty dramatic. This is a really good indicator, and we can watch this creep over time. If we start to have a little short, we can see this, and over time is relative, but 50 seconds before a major fault, you can see that start to creep. That's really good information. We can also look at phase imbalance. Phase 1, phase 2, and phase 3 are going to look drastically different when we start introducing short circuit faults. And I will show an example of this a little later. We'll see increases in harmonic amplitude in both the phase currents and the zero sequence voltage. So again, I have a diagram here of a FFT of my zero sequence voltage. And we can see that at the third order, or the third harmonic, for a healthy motor, we have a given harmonic spectrum. And then for the 2 turns and the 4 turns shorts, we can see that, like, all right, in my fundamental, I have a huge increase in harmonics. In my third harmonic, I have a pretty big increase in harmonic just from those turn-to-turn shorts. So we can start to look at those. So that's cool. We have some really good indicators and multiple indicators that show us, hey, a failure is happening. And then if we have enough of these, we can start to identify why is that failure happening and where is that failure happening. This might tell me I have a turn-to-turn short. This and this might tell me I have a turn-to-turn short in phase 1. There are also other measurements we can use to start to predict turn-to-turn shorts. We can have a data-driven version where we use big data. We can have high-frequency injections. That's more of an online technique. We can have model-based, where we have a model running in parallel. That can be offline or online. And then we have vibration analysis, where we can actually look at how that machine is vibrating. So some cool methods, and we can start to figure out not only if a fault is happening, but where and why. So I think that's exciting. Demagnetization. I apologize for the really big chart, but I think this is a good chart, and I highlighted some of the areas I think are particularly interesting. So with demagnetization, we can monitor the causes. We know the causes are temperature, and we know it's negative d-axis flux or d-axis currents. So we can monitor those two things. We can look at the flux linkage. We can look at the negative d-axis currents. And again, understand why these faults might be happening or what's leading up to these faults. Now, demagnetization has a variety of effects. We have unbalanced line currents, torque ripple, increased losses, reduced average torque, harmonics in the back EMF, reduced back EMF, and reduced rotor flux. What does that mean? In my chart over here, we have 3 different winding configurations for 3 different motors. We have no Demag in the left-hand column, some Demag, and some more Demag. All right, if we demagnetize, roughly 2%, we're seeing the RMS current in this first configuration increase 8% to make roughly the same torque. So this is a constant-ish torque scenario. So, all right, 8%, 5%, that's pretty big increase. And then we go to the different winding configurations, and now we see plus 30%, plus 30%, plus 20%. So these are very notable things to make the same torque. We could also see torque ripple. We have an increase or a decrease in 10% of torque ripple in this given configuration. We have an increase in 100%, in 70% of torque ripple in these other 2. These are things we can pick up on really easily from a measurement perspective. Even if our efficiency changes are in the single percentage points, we can track the currents, we can track the torque ripples, we can track other things really early on, so we can understand when this fault starts onsetting and how it increases with time. So I think this is pretty cool stuff. And this shows us For different winding configurations, we might need to monitor different things, but 5%, 10%, that's really easy to look for from a measurement perspective on direct measurements. You can monitor copper losses, but that's calculated. You increase measurement uncertainty. Current directly, that's a direct measurement. That's a really easy measurement to make over time and start to look at, is this creeping up? For even a very small amount of demagnetization. We're not looking at big demagnetization in a lot of these. Cool, you're experts now. All right, so what can HPK offer for motor durability testing? So we have the eDrive product, which is a data acquisition system, very accurate. We have sensors, which are very accurate, and we have some software for visualization. We offer a continuous collection of electric and mechanical signals. So you time align can have your temperatures, your CAN bus, your voltage, your current, your vibration, all in one place, your torque, your speed, so that you can understand how is my inverter affecting my torque ripple? How is my inverter affecting my temperature? And then note the changes between that. We have a really low measurement uncertainty, which means that when you do get a measurement like current, you can trust that within a pretty tight band. So if you have deviations from that, you can really note them and trust them. If you have a deviation in efficiency, you have a deviation in power, having a low measurement uncertainty will let you trust big changes. So that if it is a 2% or a 3% change you're looking for, you can trust that measurement. We have a live view of calculated values. I missed a couple letters in there, apologies. Where you can program in, these things like negative d-axis current, these zero sequence voltages, these harmonics, and you can track those and watch them live and watch if they're creeping and record that as data. If you're running a test for 80 days and you're measuring a 10 kilohertz inverter, that's a lot of data. We have some really cool data reduction techniques and triggering techniques so that you can do these long-term tests and still catch those really short events. So you can have your really long data stream trigger, have high frequency events, and really see how that inverter is functioning during some of these faults. We have feedback to control systems, so you can feedback to your dyno, your power hardware in the loop, however you're testing. And we're really proud of our local support and training so that if you're trying to do some mad scientist stuff, we can absolutely help you get there. So we got accuracy, we got data, we got electromechanical. Let's look at some examples of how this system could be used for durability testing. So I'm going to start with extended testing and data reduction. So this example on the right-hand side is actually a 5-day test where we were looking at temperatures and harmonics. And by using some of those data reduction techniques, where we were averaging total harmonic distortion over maybe at like a 20 hertz rate, we can record for days, and that creates almost no data compared to looking at megahertz data. So we can use the megahertz data to do things like a harmonic distortion calculation, store that harmonic distortion, throw that high-speed data out, and record for days on end. And then if we see a trigger, we could take that mega sample data, and you can have both the long-term test and the event of failure. So eDrive is really good for recording for long periods of time what you might be experiencing with many of your durability tests. We are electromechanical, and this doesn't show up as good as I hoped. I'm sorry about that, but we will record your high frequency inverter at a high enough rate where you can understand all those PWM switches. We'll then record the current at that high rate so you can see the current harmonics and start to tie that back to maybe torque ripple or vibration. We record the torque at up to 6 kilohertz, and if you have a higher bandwidth torque sensor, we could record at a higher rate as well. But you can get that torque disturbance and understand both the amplitude and the frequency of that torque ripple. And then we can translate that to vibrations on the shaft, vibrations on the housing, and record all of those in one place. So eDrive can measure the full system for correlation, electric and mechanical. You can start going into some deep data processing to understand all of these signals. We can do a lot of nerd stuff, and I shouldn't call it nerd stuff, but we can monitor the DQ0 for motor state. We can look at the zero sequence for faults. We can do a flux estimation. We can do real-time calculations of harmonic and harmonic phases. You can understand what the third harmonic of the zero sequence voltage is and view that as a scope trace. We can do harmonic power calculations if you think that an increase in your harmonic power losses will be indicative of failure. And we can feed all of this back to control systems. So, up here I've got my DQ0, my D-axis currents, my D-axis voltages, my fluxes, my harmonics. This is all to say, if your FEA guys, if your CAE guys have said, I think my failure modes are going to be at a certain flux level and we're going to see an increase in the harmonics, you can plug those in and you can have those monitoring live. You can trigger on those values. You can watch those values and see if they exceed a threshold. The eDrive system allows live advanced analysis and monitoring so that you can trigger on all these values. So that's some exciting stuff. If you're working closely with your CAE, your FEA team, you can have a really good conversation about how do we monitor for turn-to-turn faults? How do we monitor for demagnetization? We have a really cool measurement uncertainty tool so that you can understand, can I trust my measurements? From the measurement side, you plug in your voltage level, current level, frequency, and we give you can trust plus or minus 3 watts. You can trust plus or minus 4 watts. We have a nice tool that lets you know this is the band I can trust. So if you're looking at tolerances, you can account for that trust level in your tolerances. And this is where it comes to trusting your measurements. So eDrive lets you trust your electrical measurements for power, for voltage, for current. And we have a nice tool to help you do that. This is our measurement uncertainty calculator. And for anybody out there who's familiar with ENCODE GlyphWorks, HBK has both the ENCODE product and the eDrive product, and we work very nicely together. ENCODE is a trusted partner in durability for many applications. GlyphWorks lets you display the data, perform detailed analysis, run what-if scenarios, and do it very quickly. They're very good at data management. They're very good at processing large amounts of data, that day's worth of data. And they can augment raw data with performance indicators and compare different configurations. And we have a really nice webinar on why electrification engineers choose ENCODE GlyphWorks. I advise all of you to go watch it. Fred Kim is fantastic. But you can take these datas offline and do all those analyses that I frankly don't understand all that well. But you have the tools to do it and correlate to different fatigue methods. So HBK is really a full solution provider. I work very closely with those teams and I enjoy working with them. All right, let's look at an example. I promised everybody you'll see why I took a lighter to a rotor. So I induced some faults in a small motor because none of you will ever let me have your data or just test on your equipment. So we should work on that. But here's my little dyno. I have 2 drill motors, and I just hooked one motor up to a resistive load. So it's kind of like a constant torque dyno. I have the other motor hooked up to my inverter, which is just the trigger of the drill hooked to a battery, and I'm making voltage and current measurements on the 3 phases. In one test, I induced a short circuit fault, and as it looks, I shoved a soldering iron into the winding and I put some solder in there, and that is a induced fault. So that's a little bit of solder and a whole bunch of melting. For the demagnetization, I took a different rotor and stator, and I cooked that magnet. I mean, I got it hot. And then I put a ton of current at it, and I induced a demagnetization. Not the most scientific faults induced, but I think the data will show for itself. So what was my test procedure? I characterized the healthy state, and I just ran it through a profile of different speeds. I made sure I got certain speeds for every test. Because my dyno is this resistive load, it's basically a fixed torque and fixed current output, so I'm pretty safe there since I did not change the characteristics of the load motor. I then did the exact same characterization for the short circuits and the exact same characterization for the Demag. We can see here, this is my eDrive system where I recorded my currents, my voltages, and all my fun measurements. This is my little dyno, here's my load, and here is my inverter battery. Again, very scientific. You got to work with what you got. So what's a test example? I ran the different profiles at different frequencies from 0 to max frequency. I measured the inverter currents. These are my RMS currents, my RMS voltages. This was from the healthy test. This is a screenshot from our software. I calculated the RMS values, the power and reactive power, the total harmonic distortion, and the zero sequence voltages. And what did I see? So here I had plotted the 3 phases of healthy, the 3 phases of short, and the 3 phases of Demag for the phase currents. Well, my Demag and my my healthy look pretty similar. They're both right here. But my short circuit, if we look at my RMS current, it's just to the moon, and this is that phase imbalance. So we can very easily see that, okay, I have a turn short, I can identify that right away. That's a no-brainer. Also, if I look at my zero sequence voltage, my healthy and my Demag, with some mathematical analysis, we could probably determine that these two were statistically different, but that short circuit's just screaming, like very easily monitor for this. So we see increases in voltage, increases in current, increases in input power, increases in zero sequence voltage, and the power factor was just crazy. I wanted to plot that, but it was just nonsense, which is an indicator. How about Demag? So we can identify short circuit current. Cool, that was easy. Demag, we're going to see an increase in voltage, an increase in current, an increase in input power, and a disturbance in the zero sequence. And what I've plotted over here, I think, is pretty interesting. So again, I left this turn-to-turn short circuits in here just to demonstrate that, like, phase voltages also all over the place for my short circuit. But let's look at our healthy in blue and our Demag in green. My healthy is here, and my Demag has an increase on the input voltage. Why an increase on input voltage? Well, the flux on my rotor is smaller, so I need to provide more voltage on my stator, more voltage from my inverter to provide that same flux to get that same torque output. So we see, this is subtle, but not that subtle. We can start to see this failure creeping up. This is really cool. We can see that little tiny failure, and I'm pretty sure this was an asynchronous, but we see that. That's statistically notable. That's cool. We can also look at the reactive power. And again, short circuit current all over the place. But I've got my Demag in green and my healthy in blue. And we can see that the reactive power looks pretty similar until I get to a certain speed. And then we can see that deviation. Again, we can find multiple sources for these faults and start to identify what their cause was and where they're located. I thought this was super cool when I looked at the data, and it was like, oh, these are the same. Nope, they deviate. Really cool stuff. And this was not the most scientific test ever, but it very clearly shows this. And if you had an advanced post-processing tool and some knowledge of the FEA, you could do some really cool stuff. So with that, I went a little long in the tooth. I apologize, guys. Motors have electrical and magnetic failure modes and degradation. Motor durability can be characterized with electrical measurements, or they can at least help you understand where your failures are coming from and when they will happen. HBK offers measurement tools and software for durability and fault analysis, and it's a really cool turnkey package. You can measure battery to wheels. You can go into a software package that has a long history in durability and fatigue in Encode GlyphWorks and really do some great work. Here's the sources I cited for this. Please go read these. They're awesome. Thank you, and I hope we have some time for some questions.
I think we have a little bit of time. Thank you,
Cool.
Mitch. I'll open it up for some questions. Please use the Q&A panel to ask Mitch anything you would like. I see a question here. What types of testing should inverter suppliers be preparing for to help motor durability testing?
Yeah, that's a really good question. As the inverter supplier, I would say really knowing what your short circuit currents are going to look like, because on the inverter side, what you're worried about is, kind of inverter shorts, inverter opens. So I think knowing what the current profiles you're going to be sending to the motor in the event you have a short circuit or an open circuit in a certain phase would be helpful. Because the magnitude of the current that you're supplying is going to go into that motor and potentially cause demagnetization, cause turn-to-turn shorts, cause bearing currents. So characterizing for a given resistance, for a given inductance, what your currents will be for opens and shorts, which I would say would be the most helpful, I think.
Awesome. Probably like one or two more.
Cool.
Can you use these electrical modes to predict mechanical failures?
Yeah. So this I think comes back to like the bearing currents, where if you understand the electrical signal, you can understand why you're getting the mechanical failure in the bearing. But this also can come back to like, am I seeing an increase in vibration? Am I seeing an increase in temperature? And this is where pulling data from multiple sources, be it the CAN bus, be it physical temperature measurements, really can help you characterize that whole system, either kind of immediately or through rainfall analysis with something like a GlyphWorks.
And last question, can you periodically measure efficiency to do a health check?
Yeah, totally. And we do have people who are, every 100 hours running a brief efficiency map, and comparing those points, or you can continuously measure efficiency and actually use that as a thing you track. For demagnetization, that can be a really powerful tool. So I would say efficiency is absolutely a variable you should measure. And with the eDrive system, you really have the accuracy to trust a very tight band of how that efficiency is behaving.
Awesome. Cool. I know that was kind of a brief Q&A session. Mitch, if you want to, I think you have your contact information on the next slide. If anyone would like to reach out to Mitch directly, he'd be happy to send out his email.
I evidently do not, but I think we can put it in the chat. Mitchell.marks@hbkworld.com. Please feel free to reach out. I'm also on LinkedIn. Or if you send a message, if you scan this link with your phone, you can find a place to send me a message there as well.
Awesome. Well, thank you, Mitch, and on the behalf of the both of us, thank you for joining us today, and we look forward to your attendance at our next webinar.
Thank you, guys.
Thank you. Bye.